Hello, good people. This is video number one. I kind of think of these as leftover things. They are important, but I think the skills that we were building and the concepts that we were building at the beginning was going to take you a little bit further than these little things. Now, if we want to be mathematically proficient and correct, we should know these things. And that's what these videos are for, to kind of clean up some things and clarify some things. So it's not going to be that many videos because, especially in this first part, when we talk about properties of limits, we've been using properties of limits, right? And so when I look at all of these notations, I should say, we we notice that we've been doing them whenever we do direct substitution. We're applying these properties. And so let's see what we're talking about. We're talking about the fact that if I have a limit as x approaches some number of a function f of x, and I know that it equals an actual value L, and I have another limit as x approaches the same number c of g of x of a different function, and I know that it approaches a y value or function value called m, then what we can do is apply these rules. And we do apply these rules all the time. Excuse me. The rule that says if I'm taking the limit of two functions being added together as x approaches the same number, I can just take the limit of the first function, take the limit of the second function, and as long as those limits exist, I can just add them together. Same thing with subtraction, right? I can find the limit of two functions being subtracted as x approaches the same number c by taking the limit of the first part, getting an answer, taking the limit of the second part, getting an answer, and then subtracting those. It works as well for the product of two functions. It works as well for the quotient or the division of two functions. We can do this as long as the limits exist, right? That's what the purple and green boxes are telling you, that if the limits exist for these functions as x approaches the same value, well, then we can apply these with fairly intuitive ease, right? Like we can probably figure that out. Number five, if we're taking the limit of a constant times a function, we could just take the limit of the function and then multiply it times a constant. So I want to look at examples, the bottom examples here, because this is exactly what this is talking about. We've done this. We've done this in terms of direct substitution, and we've applied the rules without really realizing that we've applied them. So this, what the properties are saying is we can figure this out by direct substitution because we can do this. We're taking the limit as x approaches 2 of each of those pieces because we're treating each of those terms as separate functions, right? Like I'm thinking of this as f of x and g of x and h of x. So according to the properties, I can take the limit of f of x, that 3x squared, as x approaches 2 and get an answer. And I can take the limit of minus 5x as x approaches 2 and get an answer. And I can take the limit of 1 as x approaches 2 and get an answer, and then put them all together. So we've intuitively been doing that kind of without thinking, but I guess I needed you to know that there are properties that allow us to do that. And so my final answer here would be, well, let's find the limit of this part. Well, that would be 12. Minus, let's find the limit of this part. Well, that would be 10. And then let's find the limit of that part. That would be 1. And now we can just put everything together and get an answer of 3. Right? I can find the limit by just breaking it up into little pieces and treating them as functions that are being added, subtracted, multiplied, divide, and we can figure that out. As I go back up here, there are two more rules. The last rule gets a little bit dicey. Actually, all of them get a little bit dicey once the limit doesn't exist. But let's finish 6 and 7. So the rules here says if you know that R and S are integers are positive or negative whole numbers. If you know that R and S are integers and that S is not equal to 0, then when I'm taking the limit of a function as x approaches c to a power, and that power happens to be a fractional rational power, I can take the limit of the inside, get an answer, and then apply the power, provided that L to that power is a real number. So again, as long as everything works out, as long as I can find the limit of the function, and as long as the limit to that power, fractional power, exists as a value, then I can do this. Pretty straightforward, right? And then the last one, we're going to delve a little bit more into with video number 3. Says if I have a composition, if I have a function that's inside another function, and I know that the limit of the inside exists, and I know that the limit of the outside exists. And actually, that's not the complete statement. Not only does the limit of the outside exist, but it equals the function value at the inside limit. In other words, it's continuous, right? It's continuous, and the point at that x equals c value is this L value that we found. Then if I'm taking the composition, take the limit of the inside, get an answer, and then plug in that answer into the outside function, and we're going to get our final result. We'll get our final limit value. So the limit of the composition will equal f of capital L, as long as I know that capital L exists as the limit of the inside function and that f is continuous at that point. Now, these rules all apply and are all easy to do, and I really don't spend a lot of time on them because we kind of use them without really thinking about them. If I'm taking the limit of two pieces, I can take the limit of the first, limit of the second, add them together. If I'm taking the limit of two pieces being divided, I can take the limit of the top, the limit of the bottom, and then divide it out. If I'm multiplying for number 5, if I'm multiplying a number times a function, I can take the limit of the function and then multiply the number. And then, so all of these work as long as the limit exists, right? And so the end of this video is really just looking at some examples here and just letting you know that if everything is fine, these properties make your life easy. If things are not fine, and by that I mean the limit doesn't exist, or in the case of the composite rule, if f, the outside function, is not continuous, that doesn't mean that the limit doesn't exist. That means I have to delve a little bit deeper and try to figure out what is going on. So we'll finish today, or we'll finish this video by finishing these two. This is a composition. On this example here, I'm going to change colors. This is a composition because I have an inside function and I have an outside function. So I should check, does the limit of pi x over 6 as x approaches 5, does that exist? Because if it exists, and I already know that cosine is continuous on all real numbers, then I can do this step and get the answer. I can take the limit of the inside function, get an answer, and then just do the outside function, evaluate it at that answer that I get for the limit of pi over x. So I'm going to say this is cosine of, I apologize, my pen. Maybe it's time for a new pen. The lime green, if you just substitute that in there, well, that's going to give you 5 pi over 6. Oh, another opportunity for us to practice our trig values. 5 pi over 6. What is that? What is the cosine? Well, let's figure out what's the cosine of pi over 6. Pi over 2, 0. Pi over 6 is 30 degrees. Remember that this starts at 1, 0. The next one is square root of 3 over 2, comma 1/2. And then the next one is square root of 2 over 2, and then the next one is 1/2 square root of 3 over 2. But I'm looking for the cosine of 5 pi over 6. Well, I don't know what 5 pi over 6 is. This is just regular pi over 6. I'm looking at the cosine. I'm looking at the cosine. That would be the x-coordinate. So I know that this answer has to be something to do with square root of 3 over 2. But now I got to think, where is 5 pi over 6? Well, 5 pi over 6, this would be 1 pi. Is 5/6 pi less than, above the pi, or is it more than, below the pi? Where is 5 pi over 6? Or if you think about it, 5/6 pi. Well, 5/6 is a fraction that's less than pi, or less than 1. So therefore, it's probably here. That's in the second quadrant. In the second quadrant, my x's are negative. So my answer is actually negative square root of 3 over 2. That's my final answer, by the way. But what I wanted to show you was even in problems like this, we have composition going on, right? We have an inside function, we have an outside function. So we're going to take the limit of the inside, and if it exists, I'm going to take the limit as x approaches pi over 4 of 7x. And if it exists, and if tangent is continuous around the point pi over 4, then we know that we can do the step like we did above. All right, so let's check. Does the limit exist? Can I substitute here pi over 4 into my function and get an answer? That would lead me to tangent 7 pi over 4. The limit does exist. Is tangent continuous at pi over 4? Yes. All right, so then what is my answer? Well, my answer is whatever the tangent of 7 pi over 4 is. Well, I don't know what 7 pi over 4 is, but I know pi over 4 is square root of 2 over 2, comma, square root of 2 over 2. If you forgot, or if you didn't pay attention in class, I was telling you that I like to do the y values first because I know that as I go up my unit circle to pi over 2, my y's are getting bigger. So this is pi over 2, square root of 2 over 2. The next one would be square root of 3 over 2. And then the last one is going to be 1. And the x values, if you look at the points, they're getting closer and closer to the y-axis. So my x values are getting smaller and smaller and smaller. So I start with the biggest one, which is 1, and then square root of 3 over 2, and then square root of 2 over 2, and then 1/2, and then 0. I don't know. That's kind of how I remember things. I don't know if that's helpful to you. Doesn't matter because we're looking for pi over 7 pi over 4. I know that pi over 4 tangent, remember, is y over x. So it's square root of 2 over 2 divided by square root of 2 over 2. That would be 1. But then I need to figure out 7 pi over 4. Where is that? Or 7/4 pi. And 7/4 pi is 1 3/4 pi, or 1.75. Remember we said when we were drawing the unit circle that this is 0. This is 1/2 pi, or pi divided by 2. This is 1 full pi. This is 3 pi over 2, or 1.5 pi. This is like over here. Well, in the fourth quadrant, my y's are negative, my x's are positive, and when we divide y by x, we get negative. So here's our answer to that one. If you still have questions about the trig values, please come talk to me. Maybe we can practice and find another way for you to remember or to do those things. All right, last one. In the original example, I want to do letter C. According to the rule, if G is continuous and I can find the limit of f of x as x approaches 1, if it exists, then I can do this composition shortcut that says find the limit of the inside function, get an answer, and then just put that answer into the outside function. So the first question is G continuous at x equals 1? Yes, so it's a parabola. It's always continuous. Is the limit of f of x as x approaches 1, does it exist? Well, yes, because I can substitute this 1 into f, and I can get an answer. So therefore, this is equal to g of, when I substitute 1 into f, I'm going to get -4. And now to figure out the answer, all I need to do is plug in -4 into g, and I have my final result. Just erase that. -4 squared, I guess is what it's asking for. And so therefore, that's going to equal 16. When things are nice and they're continuous, which is why we look for continuity in functions, because that's the nicest situation, we can apply these properties with no issue. In video 3, I'm going to come back and we're going to talk about what happens when things are not so nice.